Hey, welcome back. Nice to see you again. What have I got for you here? Well, this is part 3 of our unit here, inverse functions, and this is using Pearson's textbook in chapter 2. And let's just have a look at some of the functions I've got here. They look very similar. One is sort of written backwards, isn't it? One is writing how to get Fahrenheit from Celsius, and then this is taking Celsius back to Fahrenheit. I wonder if you can see here that that's what's happening. If you put 25 degrees Celsius in the Celsius hole in that function, you'll get a function value of 77. And then if you let that be the domain value of this function, the range of the f function is Fahrenheit, and then if you apply this function up here, you will convert that back to the original function. So they are actually inverse functions. They're reversing the effect of each other. And probably best seen from the domain and range mapping idea, very popular with the IB, the notion of a function mapping a domain value onto a range value. Can you see these two might do the same thing? I don't know. Do you want to try it out? Let's stick x in the domain here. And so if you do f of, let's say put 2 in there, f of 2 equals 0. Let's put 2 in that function. And now, if we now take that value, this is the range value, the range value of the function f. If we now put that range value in as a domain value of g, let's stick it in there, 0, g of 0 is 2. Whoa, we've gone back to the domain value of the original function. So f and g, if you like here, like the functions up there with Fahrenheit and Celsius, they reverse each other. And that is an interesting result mathematically in functions, and that's what we're going to be looking at now. What are the, how do you do that? How do you construct a function that will reverse one? And what are the ramifications? What comes from that mathematically? So let's go down a bit here and have a look at something from Pearson's here. And the mapping diagram we just had a look at, and they're explaining it there. What we want to do now is to express that symbolically. If you have g operating on f of x, and that returns the value back again, or another notation here is g of f of x, so either of these, be aware these are alternative ways of writing the composition of two functions. And if you get x back again, what are we saying here? G operated on f of x, so and it gave x back again. So f of x gave a range value for f. Then g came along, took that range value and went back to the original domain value that was put in f, going backwards. So it's undoing. There's another bad way here. Pearson's saying one undoes that. And so we're going to investigate that in a minute. Down here, a little bit of idea of inverse operations. Because in constructing an inverse function, we'll want to reverse all the steps that have been done on the domain values in that function. So if we've got a function f which takes x and adds 6, to reverse that, g of x is an inverse function. If it takes that result and take 6, it will return the x back again, return us to the domain value of the original function. So we know addition and subtraction are inverse operations. Multiplication and division are inverse operations. So we're going to want to use this to reverse the effect of one function and undo it and create its inverse. So let's come down, and here's the definition. I'll put it here. Definition of the inverse function. So here, it's got to be such that f operates on g and returns x, and it's got to work the other way. G must be able to do the same to f. So it doesn't matter which of the pair of inverse functions you do first. If you do the other one after, it will return x. It will undo it. Hey, and this is something interesting. The definition of, or the symbol, sorry, for an inverse function is f neg 1. And this is a little bit confusing. Now, you know the neg 1 exponent really means 1 over 2. So I suppose it means the reciprocal or the inverse. But when you use f neg 1 of x, it doesn't mean that index method. We use the idea of it's still the inverse, like it's the inverse of 2 is reciprocal of 2, I said 1 over 2, but f neg 1 means the inverse, not 1 over. So there's a bit of a conflict there with the f neg 1 notation and the index use of that here. So here on functions, a superscript up there does not mean the same as it does in index land. That's one of the few ambiguities, I suppose, that you do encounter in maths notation. Usually there isn't any. But a superscript of neg 1 in function land means you're talking about a function which will reverse the effect of function x. You are not talking about 1 over. Okay, so here's our definition here. F operate on its inverse will return the effect of f back to the domain value x. Or if we did it in a different order, if we applied the inverse of f to f, then it will reverse the effect of f and give us the domain value back again. Now, obviously, this must be true. When f starts out, over here the domain of f, it produces a range value, the range of f. Now, the inverse must obviously be able to operate on this result. This becomes the domain of the inverse, and that's going to return us back to x. So the range of the inverse is the domain of the original function. It's going to reverse it. What do we do to see such elaborate pairs? Let's find the inverse of a function. So can you find the inverse of the function 4x take 8? So we want it in either direction to reverse the effect of the other function. So here, basically, we've got to undo all these steps. So let's have a look at the operations. You can actually see there we're going to switch domain and range. So what one way of that is doing is to switch x and y in the formula, reverse it, so that when we do the operations you're going to get the other one back again. So state the function, replace f of x with y. It's easier. Interchange x and y in the formula. So we're going to switch the domain and range. That's going to give us our reversing effect. Reversing or undoing what's happened there. Reversing or undoing. So then we would have this thing here. I don't like the way... they've rearranged it here. So interchanging x, this is okay. X equals 4y take 8, and then rearranging, they put it on the other side. You could put rearranging this, x plus 8 equals 4y. They've actually done that in another step and put 4y equals x plus 8. That's all right. And now, because functions are always written as dependent variable equals some operations done on the independent variable, we always make y the subject of the formula. So there it is. And then you must. Notation in IB is very important. You can't leave y equals. You have to explain that your new y is your inverse function. Okay, so the inverse function is f neg 1 of x. That's a symbol for a function which will undo f of x is a quarter x plus 2. So that's an important set of steps. So going to in Pearson's, they summarise this later on. Let's come down and have a look. Can we verify or check that that works? Well, let's do f on the inverse function. Remember, the inverse function from just up the page there is a quarter x plus 2. Now, theoretically, if you do f to that, you will reverse it. what was f of x? What was f of x? F of x was 4x take 8, if you remember. Just go back up there. See, up there was 4x take 8. So let's do f on its inverse, and one should reverse the other. So we're going to stick a quarter x plus 2 in the x whole of f. F is being done on the inverse. So instead of x in there, we're going to put a quarter x plus 2. So instead of x in the statement, we have to put a quarter x plus 2 as well. So there, Pearson's gone across the page there and shown that you get x back again. Let's do it the other way, because it should work both ways. Let's apply the inverse function to 4x take 8. Well, the inverse function was a quarter x plus 2. So if we apply the inverse function to f, if we apply it, f was, instead of x in here, f was 4x take 8. This is composition of functions work. So we have to stick 4x take 8 in there, a quarter 4x take 8 plus 2, which works out to, again, x plus 2 take 2, which is x. So it works. It undoes the function and gives back the original variable domain value that you put in. So it has been confirmed that because these do that, one operator on the other in either direction gives x back again. They are stated as inverses of each other. All right, so if you think about what we've done, change the domain and range, then reversing them produces the opposite number. So an ordered pair on y equals f of x, when you change it around, will be b and a. It will reverse the positions. X and y will interchange. If we map that on a Cartesian coordinate system, AB, when we interchange x and y, becomes BA. What does that mean? Well, that's actually a reflection in the line y is equal to x. So in interchanging x and y, swapped, if you like, in the formula in f of x, it implies that a point AB in the mapping that f of x does, f of x will take A and maybe map it on to B. That then becomes, in f negative 1 of x, BA. B will be mapped back onto A. They change positions. So the big upshot of this is that there is a graphical result. We've just been doing the algebra, changing x and y. But graphically, what does that mean? It graphically means all points on f of x are reflected in the mirror y equals x to give points on the inverse of f of x. So the two graphs, if you graph the function and its inverse, would be reflections in the line y is equal to x. That's the theory. All we have to do is actually apply that a bit. It's not too hard. Graphical symmetry of inverse functions. There we are. We just stated that. So if this is the original function, all points here, because they have the x and y changed, are not quite reflected there. When the x and y changed, become this graph here. So the inverse is a perfect mirror image, using y equals x as a mirror, of the original function. All right, the identity function, we don't use this very much. The identity function is just x, what we go back to. You come back to an identical function. So if you said the identity I of x, what function doesn't change the x value when you pump it into it, leaves it identical? It's just the function y equals x. If you put any value into y equals x, the y value becomes the same. So it actually doesn't change. It's an identity element. Not all that important, but worthwhile noting that terminology. Alright, so let's have a look at the existence of an inverse function. The problem is, an inverse function, you think, well, all you have to do is interchange x and y and you'll get a formula. But what we have to do is to make sure it's a function. Is the result here, is this result an actual function? So in other words, for each x value there's only one y value. Let's have a look at starting with the function x squared plus 2. Here we go. Put y equals, interchange x and y, get y on one side as a subject of the formula. There it is. Y squared equals x take 2. Or y equals, down here they made a little bit of a mistake here. Oh yeah, have they? No, there it is, that's alright. So y equals plus or minus root x take 2. So there's positive root of x take 2 and negative root of x take 2. So this is the graph here of y squared equals x take 2. What do you notice? We've done all the processes, we've interchanged x and y back over here. This is good work. That means this has been reflected in the line y is equal to x. Good work. Oh, but hang on, this is not a function, because for any x value here there are two y's. So the red line is not a function. So we can't say that's the inverse function. So it's not a matter just of doing the process. You must check whether it's a function. Check its function status. Okay, so they obey all the rules here. Interchange x and y. One's a reflection in the line, the graph of one is reflected in the line y is equal to x of the other one, but it isn't a function. So in this course, what they will do is only give you functions which are one-to-one, or they will restrict the domain, so when you do the process of getting the inverse function, it will be a function. So here you can see why it doesn't work, because a one-to-one function is when for each x there is only one y, but for each y there's only one x. So that this is not a one-to-one function, because the y is made up with two different x's. And when you reflect it, that means the x's will match up with two different y's, and it won't be a inverse in that situation. So this is what they've said in the syllabus they will always do for you. They will restrict it, so you've only got half the function. Right, so this is, if you like, one-to-one, because you've cut out the other side, which is going to give you down here when you reflect in the line y is equal to x. This is the problem bit, because you've got two pieces that are going to give you two y values for each x value. So they will restrict the domain. It says that in the syllabus. They will tell you only to consider half the function, so that when you actually reflect it, that will be a function. But that's why they're going to tell you to draw only half of it in some cases. Alright, definition of a one-to-one function, not that important here. It's a one-to-one function is such that when you go up the x vertically, only hits once, and let's draw something like that, and if you do go across horizontally, only hits once. So it's one-to-one. In x land it only produces one y, and in y land it only produces one x. Then it has no problems with its inverse. Its inverse will be a function as well. So here we are. This is typical of what we expect this year. X squared plus 2, only x is greater than or equal to 0. So you draw it, so you don't have a problem here, no problem here, because when it's reflected in the line y is equal to x, there is only this part, so each x relates only to one y, is mapped onto only one y, and that's okay. You haven't got the problem bottom half because you've restricted the domain, only taken half of it. Alright, so you might read through this, pause the presentation, read through it, or read through it in the textbook, Pearson's explanation of that. So that's what they will do, restrict the domain, so that when you do the process, it works, it does give you a function. Okay, so here we are. You could restrict the domain differently. Take x is less than or equal to -1. So that's just, this keeps going, so that's only that bit of the function. So if you change x and y in the formula there, you'll be effectively reflecting it here from there, and you can see the domain and range change. So the domain is x is less than or equal to -1, and that will be the range. The range will now be y is less than or equal to -1. The range was, in this one, y is greater than or equal to 3. That becomes the domain. X is greater than or equal to 3. So they switch. So up here, let's say what this is. Y is greater than or equal to 3. That's a range. X is less than or equal to -1. So down here, the pair become y is greater than 3, now becomes x is greater than or equal to 3. X is less than or equal to -1 becomes y is less than or equal to -1. So the range and domain interchange because x and y are being interchanged. So that's important to note there. They will always, in this course, give you, for finding the inverse, a one-to-one by restricting the domain. Okay, and you can talk about those. All right, so finding the inverse, what do you do? Here we are, we've done that. Confirm that it is one-to-one. In this course, you can assume this, they will restrict the domain. Replace f of x equals with y equals. Interchange x and y. Make y the subject of the formula. Then when you've found the inverse, don't use y equals, use f neg 1 to emphatically say, I've found the inverse of f. And just remember, if you're talking about domain and ranges, they interchange. Let's do one here, getting to the end here, and take too long here. Example 15. Okay, x is greater than or equal to -3. So determine the inverse function. First of all, put y instead of f of x. Interchange x and y. Alright, that goes there, and that goes there. Then try to make y the subject, so we have to square both sides. X squared equals y plus 3. Take away 3, y equals x squared, take 3. And then make the statement f neg 1 of x equals, or f neg 1 such that x maps onto x squared, take 3. Be aware that this line you should understand and be able to use. The other way of doing it is just to write it like that. But the IB expects you to use all aspects of language in mathematics. So there we are. Now what's the domain and range? Well, the domain of the inverse is the range of the original function. What was the range of this original function? Well, it's a positive root. So y is going to be greater than or equal to 0. And so that becomes the domain of the inverse, because when f operates and produces this sort of value, f neg 1 has to pinch that, becomes the range, and give the domain back again. So you might add down here, what would the range be of the inverse function? The range, well, that's the domain of the original one. So that is y is greater than or equal to -3. Okay, so you can interchange them there. Okay, well, let's have a look now at doing it on the calculator, and Pearson's has used the TI, and I want to put in here in the Casio the two functions. Here you are, the one that we started with in graph mode there, and its inverse, and also the line y is equal to x. And yes, we give this a tick One is a reflection of the other. I've used here the view window setup, not square, so you don't quite see how that's a perfect reflection due to the different different scale size on the X and the Y axis here. So it doesn't look perfectly where I haven't squared up the window. You can actually check points, however, because if you go shift F5 to in here, G-solve, go up there, you can actually do an X-calc for the function x take 3, and if you put in y is 2, you get x is 7, and reversing it over here for the function toggle, you've got to toggle to the function and do a y calc for an x of 1, and you get a y of 4, and so on. So you can actually check that. I haven't checked those two exact values here. I really should have put in here x is 7 and checked that. No, sorry, have I got that right? Yeah, so here put x is 2 and get a y of 7, so I haven't made them match here. But you can check that inverse relationship between the two. All right, so play with your calculator, have a look at what's going on there, see what you think. Here we're trying to find another example of g of x and its inverse. So same thing, just check that. Replace f of x with y, interchange them, got to rearrange a bit of algebra there, make y the subject. There it is, and then use the G notation. Never leave it as y equals. You must use notation to indicate that you have achieved the inverse. G was originally a linear function. Do you get that? It's a third take a third of x if you write that in full. And you can have any x in there. X is a member of R, and its range is y is a member of R. And so its inverse is the same, because the domain of the inverse is the range of the original function. The range of the inverse is the domain of the original function. So let's go down and solve now f of g neg 1, or f done on the, here f done on the inverse of g. So we've made up the inverse of g. So now we want to have f operate on it. We better just go up here, because f, what's f do? I'll write alongside here. F of x does 2 times x plus 4. So if f is operating on g, the inverse of g, you've got to stick the inverse of g in the x hole. So what does that mean? You've got to stick neg 3x plus 1 in that hole. So here it is down here, pity it went to another line. It becomes 2, and in here, in place of x, neg 3x plus 1. So this notation is quite easy to understand. Whatever's after the function name is a variable statement. What's going to be used as a variable, and you put the result of g in there. And so we get this line here. Okay, so solving that, you could actually then simplify that one down there. All right, so doing it the other down, well, I've repeated it here. I've repeated the solution there. So here, keeping on going, we've got 4/3 as the numerical answer to that. All right, let's have a look at example 17, and then we'll try some. X squared takes 6x, find the inverse and state its domain. Well, you actually have to, you can see here, with x squared takes 6x, you can't use this because when you invert it and make the inverse, you're not going to have a function, so we have to restrict the domain. You won't be asked to do this, they will do this for you. So here they've suggested we go from neg 3 to 3, Why? Because from -3 to 3, 4x squared takes 6x, gives us, they're going, x is greater than or equal to 3. So we're starting here. So that is a one-to-one function, and when you do the inverse, here it is here, then rearrange it, we get plus or minus, but here it will only be the positive result. So let's go through this. Change y and x, get y by itself, x by itself. This is a bit harder, have to factorise that, and then take the root of both sides, and then we're only going to use the positive root because it's over here at x is greater than 3. So what they'll do is actually change the domain for you. You won't have to work that out, because when you actually invert this function, this one must be a one-to-one, so you can't have the rest of this function up here. This one has to be an actual function, so the original one has to be one-to-one, no duplication of y values. Alright, so the inverse is that, and the domain of the inverse is the range of the original function. What's the range of the original function? Here we have it here. There's the original function. The range is y is greater than or equal to -9. And so the domain is x is greater than or equal to -9. Alright, so it's confirmed graphically because one is, when you plot it accurately, reflected, the graph of one is reflection in the line y equals x of the other. Alright, what can we do? Well, let's do some problems. So there are some there, you can pause it and look at those, and there are some more, of course, just going down there to number 29. So you can just pause it and work through a few there, and then down the bottom I've chosen the fully worked solutions from Pearson's, which is very good, and so I'll show you that, so you can toggle back and forward. So let's do it in sections now. The first section going from question 1 down to 6. Give you a chance to actually pause that later on, study whether you got them right, and then from 7 we'll go down to around the bottom there to 8, and just pick that up. Notice that Pearson's have used the TI input there. The graphs are going to be the same on the calculator, just the input into graph mode on the Casio is a little bit different. Let's just pop down here, down to the bottom of 11, just give you a chance to pause it at the appropriate spot, and then 12 to 16, have a look at those. As you do a problem, it's worthwhile toggling on, you'll get used to it and pick up the answer. 17 will just fit, we'll just go here, 17 to 21, 22 there. It is a bit hard to follow Pearson's when they write across the page. Mathematically it's better to write down the page. So I think we can get them all on. 29. We'll just do to there. 24. And then we'll come down and finish off with 29. So you need to pick up those pieces after you have had a go at the problem. So what we'll do is we'll go back up. So you might want to start there when you're doing the problems, and then toggle down. Alright, look, this is building up quite a nice background in the theory behind functions and how they operate, domain and range. Please watch the notation, terminology, and be able to discuss domain and range as we get on to inverse functions and so on. So the unit's coming along nicely. I hope you're enjoying yourself. So at the moment, from me, it's cheers for now. Catch you in the next presentation.